So hello, my name is Victor Brar. I'm a professor here at the University of Wisconsin who works in condensed matter physics. And I will be showing you today the various experiments going on in many groups here at the UW that work in condensed matter as well as biophysics. So just to give you a little preview of what we're going to be talking about, condensed matter, broadly speaking, is the study of physics that occur in materials. And it actually encompasses a huge space of physics. So it includes particle physics phenomena. So the Higgs boson was first described in condensed matter systems. Positrons were a particle that were first observed in condensed matter, as well as Majorana fermions and other similar exotic phenomena known in particle physics. In addition to those types of effects, condensed matter also includes semiconductors, superconductors, materials used for quantum computers, magnetism. So many of these groups here study those types of effects. It also includes fluid mechanics and biophysics and the various applications of materials. So there's really a lot of different types of experiments going on that we broadly call condensed matter. And before I go into the details, one unique thing about it is that most of these experiments I'll be talking about are tabletop experiments. So if you do your PhD in condensed matter, often you'll design your own experiment and you will grow your own material often and do the whole setup and measure it yourself in a lab. So these are not experiments that involve collaborations with thousands of people. You just get to own your own experiment when you do a PhD in condensed matter. So I'm going to start now talking about the various groups here that work in condensed matter. And I'm going to begin by discussing the theorist. So we have a few theorists here who condensed matter physics. One of them is Bob Joint, and his work focuses in a lot of different areas. So he provides a lot of assistance to the quantum computing groups, but he's also into some of these exotic materials. And one example is this material, zircon tellurium 5. And this is an interesting material because the electrons that move through this material behave like Weyl fermions. So these are a special type of particle. They have a linear dispersion like a photon, but their spin is a little wacky. And even though you can't observe them in free space, you can observe them in materials. And this particular material shows them. And if you apply a magnetic field, you can see that the resistance of this material changes due to the behavior of these electrons that move through it. And Professor Joint has done a lot of the theory that solved this problem. He's come up with theories that explain how these particles are moving. These are scale invariant theories that describe the experiments pretty well by modeling the electrons as these Weyl fermions. Professor Alex Levchenko is another theorist here. He works on a number of experiments. He collaborates with many experimental groups and provides theoretical support for them. And I'm just going to describe two of his interests here. So one of his experiments, or one of his interests is looking at materials where the electrons move through the material as if they're fluids rather than free particles. So in a lot of materials that groups are discovering these days, the electrons move almost like honey through, you apply a voltage and the electrons flow more like honey than water. And he's come up with theoretical explanations for why that happens. And he's also come up with a few predictions that these groups are looking for. Another one of his experiments, or one of his efforts, is to is to describe experiments where some of the electrons that move through a material have negative charge and some have positive charge. So I think at the beginning I said that the positron was first discovered in material. These are just basically electrons that have positive charge. We call them holes. And if you have two materials, one with holes moving through it, or positrons you could call them, one with electrons moving through it, the negative charge in one attracts the positive charge in the other, and you get very strange sort of transport behavior. In fact, you have current that flows that carries no charge at all, and Professor Levchenko studies those systems. Professor Vavilov, in collaboration with Mark Erickson and Mark Friesen here, studies Majorana particles. So these are particles that They haven't been observed in free space, but in materials they have been observed. And these are particles that are their own antiparticle. So instead of an electron and positron, in this case, it's a particle that's its own antiparticle. And he's come up with predictions for certain types of material systems. So if you grow a material just right and pattern it in just the right way, he's predicted that the electrons that move through that material are going to behave like these Majorana particles. And he has collaborations with a number of groups that are trying to make the devices that he's predicted to see these effects. Okay, so Professor Robert McDermott, a big part of his effort is obviously trying to make a quantum computer. And if you've watched the quantum computing talk, you've probably seen some of those experiments. But a big part of that effort is in improving the materials that cause decoherence in quantum computers. So currently, quantum computers just don't have long enough coherence times to actually make scalable, full-scale quantum computers. And part of the problem is just that the materials have defects in them. So what he does is he makes qubits out of different material systems, and he studies how those qubits dephase over time. So these are experiments that occur over hours here. You can see the qubits are dephasing, and each one of these is made out of a different type of material. And he can figure out what's going on. And in this case, he sees that there's quasi-particles. These are electrons that are interfering with the superconductor. And he can study their behavior, and he's trying to figure out how to engineer these qubits in a way that are free from these material defects. Professor Jen Choi is another professor here. She's actually in the engineering department, but she has a joint appointment in physics. So if you come here for a physics PhD, you could work for her. And her group specializes in making very powerful sensors, quantum limited sensors, out of atoms and out of defects in materials. So in one type of experiment, she'll trap rubidium atoms in these vacuum cells. These red dots here are some glowing rubidium atoms. And she traps them in free space, and they interact with magnetic fields. And by doing spectroscopy on those rubidium atoms, she can actually measure magnetic fields very, very precisely. Now, she also does similar experiments on defects in diamonds. These are NV centers in diamonds. She builds devices where the diamond defect actually can be used to measure magnetic fields or electric fields in the nearby vicinity. And to do these experiments, you actually have to build new instrumentation. So if you were to work in her lab, a lot of your efforts would be involved in building very complicated apparatuses to trap the atoms, for example, or to do spectroscopy on these defects. So Professor Rzchowski works on complex materials. So he works on material systems. In this case, these are called complex oxides or complex nitrides, where the crystal structure is very complicated, and the electrons move through these materials in very strange ways. In the case of this material, strontium iridium oxide, the electrons show a behavior called the spin Hall effect, where if you pass current through the material in one direction, all the electrons will acquire one spin, and if you pass it through in the other direction, all the electrons will acquire a different type of spin. And this is due to spin-orbit interactions. He's been studying this, and he's figured out some of the reasons this effect occurs. And he's been looking at how to change the crystal structure of the material to modify this spin Hall effect. Now, he's also observed that this effect occurs, the spin Hall effect occurs in this magnesium gallium nitride. And in this case, there is no spin orbit interaction. So he has ongoing experiments to try to figure out why this spin Hall effect might be occurring in this other material. Now, he also studies these electron hole systems. So when I described Professor Levchenko's work, I think I mentioned that he looks at materials where you have some of the carriers are electrons and some of them are holes or positrons. And these have negative charge and these have positive charge. And if you run current through this, you get zero charge passing through it, even though the electrons are moving. Well, Professor Rzchowski tries to actually realize that experimentally. He grows this material called strontium titanium oxide along with aluminum oxide. And he's shown that he can create systems where some of the carriers are electrons and some are holes if he grows the structure in a very precise way. And he's been tuning this to try to make these novel effects occur to a more powerful degree. So he's changing the crystal orientation of these complex materials to try to make this dual electron hole carrier phenomena more robust and possibly something that could be used in real world devices. So Professor Bergman is the newest addition to our department who works in condensed matter. And his experiments, many of them take place at the Stanford Linear Accelerator, where he develops ultrafast spectroscopy methods. And a lot of what his work focuses on is this. So if you have a LED, so a gallium nitride LED is a blue LED, and you run current through the LED, well, what happens? The electrons lose some of their energy and they release these photons. But it's not exactly known precisely what's happening. These electrons are actually moving at very fast timescales, 50 femtosecond timescales. And what Professor Bergman's trying to do is create tools that can actually measure these ultrafast dynamics of electrons that move through these materials. And this is done with X-ray spectroscopy, as well as some other methods. So one of the materials that he wants to look at is molybdenum telluride. And this is what one of his typical experiments will look like. He shines a very fast optical pulse on the material, and then he probes it with another short wavelength pulse. In this case, it's not quite an X-ray. It's what you call an extreme UV pulse. But it's good enough to do spectroscopy on this material and to observe the electron's decay as he changes the time between these pulses. And he's actually already observed a few interesting effects. Again, these are experiments that take place at the University of Wisconsin. He's seen how the holes in the electrons move at different rates. So he takes snapshots in time of how many electrons there are and how many holes there are at different energies. And he sees them change as a function of time by varying the time between those two pulses. And by doing these experiments, he can actually track the carrier dynamics, and he can figure out what's causing the electrons to behave differently than the holes as they move through this particular material. Now, like I said, he also works at SLAC, which is a linear accelerator in California. And there he's developing very powerful X-ray laser methods where you can watch a crystal evolve in time by using these ultrafast X-ray pulses. So they're constantly trying to make these X-ray lasers go faster and faster and faster. And he's developing new types of systems that can make these X-ray pulses more compact and closer together in time. So my lab, as I said, I'm a condensed matter physicist, and what my lab works on is scanning, tunneling spectroscopy of 2D systems. So what is scanning tunneling microscopy? It's a type of microscope where you bring a metal tip very close to some material that you want to study. And if you scan the tip around, you can measure the current that flows from the tip into the surface, and you can actually get atomic resolution of the surface. So this is an atomically resolved graphite surface. There's a honeycomb lattice here. And on top of that, you can actually move atoms around. So here I have a movie where my PhD student in my group grabbed these carbon monoxide molecules and moved them around on a copper surface, and he created what's called a quantum corral. He arranged them in a circle. And you can actually see the electron waves in the copper crystal scattering off these carbon monoxide molecules. So we can actually see the electron wave function when we do scanning tunneling spectroscopy. So for example, here's the short wavelength electrons. Here's the long wavelength electrons. And what my group is interested in is using this technique to study 2D materials. These are atomically thin materials. So we actually create our devices using Scotch tape to peel off individual layers of atoms, and we can stack them on top of each other in different ways. And depending on how we stack them, we can realize a number of interesting effects. So we can create hydrodynamic flow, where again, the electrons are flowing kind of like honey. We can create new magnetic orderings. And then there's other novel phases that can occur. And we can also study defects in these materials. So here's an individual charge defect in graphite, and we can probe it with STM, and we can see how the electrons scatter off this defect. And these defect studies are particularly important for quantum computing. So here, by the way, is a picture of my STM. It's a tabletop experiment you can't actually see, well, here's an image of the tip approaching some crystal. The tip is actually buried inside this little walker here. But we've attached lenses to this STM so we can actually shine light in and shine light out, and we can take images like this, and we can also do spectroscopy, optical spectroscopy on whatever's underneath the STM tip. And what we're interested in looking at is defects, what we call quantum defects in materials, where the individual defects in some crystal lattice behave like a isolated atom that can emit a single photon at a time. It can emit entangled pairs. And we're trying to find material systems that do that. So again, we can move the atoms on the surface and create new optical phenomena by patterning them. And then we can actually shine light in and do spectroscopy on these individual atoms that are inside our STM. Now, my group also does some applied physics experiments. So in this case, what we do is we try to make materials that could be useful for futuristic space propulsion applications. So currently all spaceships that go into space have to carry all their fuel with them, but there's a lot of groups, there's significant effort right now by NASA and other private foundations to create spacecraft that are actually propelled by a ground-based laser. So these groups are building a 100 gigawatt laser in Chile. They're gonna shine it into space and try to push spacecraft around. And the problem is that you need to make a material that can reflect this light without melting. And you want to reflect a lot of the light because you don't want this thing to melt. And we actually get our inspiration from nature. If you look at a butterfly wing, it doesn't actually have any color in it. But if you look closely at it in an electron microscope, it's patterned kind of like this. There's this nanostructure to it, which is very similar to a diffraction grating, which causes the butterfly wing to reflect with really high efficiency. And also to create a whole spectrum of colors, which makes butterflies beautiful. So my group is actually making surfaces like this. This is a nanofabricated surface that can be used to reflect light in very particular ways for space propulsion. So first of all, we want to absorb none of it. We want to reflect almost all of it so the thing doesn't melt. And second of all, we want the optical forces on this cell to be such that it doesn't fold or bend in some way. So we designed these things on supercomputers, and we're actually now fabricating these surfaces in real life in the clean room at University of Wisconsin. Okay, so finally, Pupa Gilbert is a professor here who works on a unique area of physics. So this isn't physics. The materials she looks at aren't necessarily things you'll find in a physics textbook, but it really takes a physicist to understand them. So she looks at biomaterials. These are materials that can be found in clamshells, shells that are found in the ocean. And she looks at the ordering of these shells, and she tries to figure out what causes them to grow in a particular way and how they're ordered. So if you work in Pupa's lab, you would actually do your experiments at a synchrotron in Berkeley. You'd be traveling to Berkeley probably 5 to 6 times a year. And you'd be using these new methods she has to study these types of materials. So one example is the exoskeleton of a sea urchin. So if you look at a sea urchin, this is a cross section of one of these spines. And this is actually a nice crystal lattice, but it's grown by some proteins some proteins that are secreted by the sea urchin that cause it to grow in this particular way. And she does this very unique spectroscopy method to try to figure out the various ratios of these proteins to figure out which one was activated during which point of the growth. And she can figure out exactly what's causing the ordering of the sea urchin spines in this particular way. Again, she does this all in a synchrotron in Berkeley. And she repeated this technique on coral. So she's also looked at the exoskeleton growth of coral, and she's found similar mechanisms. She's found that these two proteins are driving the growth of the coral skeleton, and they're doing it by precipitating ions out of seawater. And she can see how the seawater chemistry affects the growth of these things. And one of the interesting things that she found is that as the seas get warmer, it may not be as drastically bad for coral reefs as some people have expected. The acidic seawater doesn't affect this particular growth mechanism that she discovered. Okay, so like I said, condensed matter covers a lot of different areas. This particular area would be called biophysics. And we have a lot of different types of experiments going on in the department. So I would encourage you to set up meetings with the condensed matter professors here. If you're interested in these types of experiments, send us emails. And obviously I encourage you to come to University of Wisconsin. So that's all for my presentation here, but again, please email us if you have more questions. Okay, thanks.